Welcome to Lecture 2.2c. The last part of Section 2.2 is about something called end behavior, and so these three videos are going to explain the end behavior examples and the idea behind them. I'm actually going to try something a little bit different for this one. Normally in these videos I start by explaining the big ideas, kind of what these objectives mean and how you should think about them. But I've noticed in class that some students have actually struggled to articulate those ideas, and I wonder if maybe that's because what you heard first in the video gets lost when you get to the end and do the examples. So instead, we're going to start in directly with an example, and then we're going to take a bigger look later in the video thinking about the ideas behind what we just did. You do need to know this definition in order to do the first example, so pause the video now, copy it down, and then when you hit play, I'll show you how to prove that g of x is a right end behavior for f of x. Great, so in this definition, it's a pretty simple definition. We have two functions. Just keep in mind that f of x is always the function that we're actually interested in, and g of x is usually going to be a simpler function, so you can use this first example to kind of gauge the difference between the two. We want to prove that g of x is something called a right end behavior model. And there's a really simple formula for proving that. Basically, we calculate this limit. If the answer is 1, then g of x is a right end behavior model. Here's what it looks like. So I set up my limit, and I've got f of x on top and g of x on the bottom. And to evaluate this limit, our instinct is always, well, can we plug in the c value? If we plug in infinity, we obviously can't do that, so we're not thinking about just plugging a number in. We are thinking about what happens when x gets really, really large. And looking at this, I can tell the top is going to get really, really large because we have x to the fourth, and the bottom's going to get really, really large. So this is one of those infinity over infinity situations, which we in class said that we can't really know how to solve. Well, this is actually one that we can solve if we use an algebra trick. I'm going to rewrite this limit just using a rule of algebra, not using any special facts, but I know that when you have a single denominator and many terms as numerators, we can split that into many fractions. So it's going to be 3x to the fourth over 3x to the fourth minus 2x cubed over 3x to the fourth, so on and so forth. So we end up with this long fraction. If at first glance this doesn't look like it's helpful because it looks more complicated, just bear with me for a second. Now notice that this is just an algebraic manipulation. If I added and subtracted all these fractions together, since they have the same denominator, I would end up exactly with that. And so that's how I can confirm that I'm allowed to take this step legally. Now another thing I'm allowed to do legally is just to use any algebraic simplification rules. In particular, I know that 3x to the fourth divided by 3x to the fourth is just 1. And if I go ahead and simplify all of these other fractions, we have a number of x's that will cancel each other out. So this becomes 2 over 3x. And this term becomes, the 3's cancel out, so it's really just 1 over x squared. And then we've got 5 over 3x. And oh, this should be x to the fourth right there, so this is x cubed. And 6 over 3 canceled to 2 over x to the fourth. Again, you may not initially see why this is helpful, but let me just point out that we're taking a limit as x goes to infinity. And you know something about terms that have x's on the bottom as x goes to infinity. Each of these terms, in fact, when we plug in really large x values, is going to end up giving us a value that is a really small decimal. And actually that means that all of these terms are eventually going to go to 0, except for that first one, which is exactly what we wanted to happen, because this is really just the limit as x goes to infinity of 1. In other words, this really just equals 1. Because I can show that each of these individual terms, and in fact if you wanted to you could split it into multiple limits. I'm a little too lazy to do that here, but you could see it really clearly as each of these disappear. So since I made the fraction with the two functions and the limit of their quotient equals 1, I've just proven that this function g of x is a right end behavior model. If you want to do a left-hand behavior model, you would use the same process, but you would take the limit as x goes to negative infinity. In fact, you're going to do that right now. Pause the video and solve the one that's for you. Great, so hopefully that wasn't too hard. Here's what my work looks like, and notice that I did take the time to actually write out the intermediate step at the end. Remember that you can only split these limits if each of these limits is defined and is a specific number, isn't going to infinity and isn't undefined. But that works out fine for polynomials. So sure enough, the limit of the quotient equals 1, which means that g of x is an end behavior model. Now, hopefully you've started to notice something about the end behavior models. There's a relationship between 7x cubed and the polynomial on the top. And that relationship, if you notice, has to do with the highest degree. So we're going to use that relationship instead of just to prove end behaviors, to also find or to guess and then check end behavior models. Look at the top polynomial and see if you can predict an end behavior model just for the top polynomial. Okay, now do the same for the bottom. And thinking about what you would have predicted, here's what I'm going to propose is an end behavior model for this first function. Notice that I've chosen the highest degree term from the numerator and divided it by the highest degree term from the denominator. Now, in order to prove that I'm really right, I'm going to use the same strategy we used before, which starts by setting up this limit. And because I have a rational function here, instead of writing it as a fraction over a fraction, I've just chosen to use a division symbol instead, but it's the same idea. Here is f of x, and we're dividing it by g of x. Of course, I know that dividing a fraction is the same as multiplying by the reciprocal, so I've just taken an algebraic step here to simplify. And then I'm going to take another algebraic step. This might be the one that's a little tricky for you. What I've done is I moved the denominator of the second fraction to be the denominator of the first fraction and vice versa. The reason I'm allowed to do that is because I'm multiplying these fractions. Think about it this way. If you were to take this expression and multiply it, top and bottom, you would get the same thing as you had in this expression. So I can prove that this is an okay algebraic step because they simplify to each other. Now, the reason I did that, if you're thinking forward, is because now I start to see that same pattern. Remember, our goal is that this limit is going to equal 1. Well, this looks pretty familiar. That's very similar to the proofs that we did at the beginning of this video. And actually, this step here that I did was I changed multiplication back to division, which allowed me to flip this fraction. And the reason I did that is because when you have multiple terms in the denominator, I'm not allowed to split this into multiple fractions. However, if you have a single term in the denominator and multiple terms in the numerator, I can take this fraction and split it into a bunch of fractions, which is what my next step was. And the goal here is to see that fundamentally, as we go to infinity, a bunch of these terms go to 0. This one goes to 0 because we have a higher degree on the bottom than the top. Some of those x's could have simplified, but I'm going to go ahead and just go straight to recognizing that that will go to 0. This will also go to 0. This will go to 0, as will this one. And so we're left with the limit as x approaches infinity of 3x to the fourth over 3x to the fourth. But that's just 1. So really what we have here is 1 minus 0 divided by 1 plus 0 minus 0, which is really just 1 divided by 1, and the limit is 1. Notice that I stop writing the limit at the step where I evaluate. So this little curly Q thing is technically not really an okay algebraic step. I'm just using it to signal the fact that once we take the limit, it's going to equal 0. I couldn't have just crossed it out and put 0 there unless I was also evaluating the rest of the expression. Anyway, this 1 right here, that proves that we've got an end behavior model. And this is it. Try using the same steps to do the one that's for you. When you hit play, I'll show you what the work could look like. If you need to, go back and look at my work, because I know I went through it a little bit quickly, but it's all just little algebraic steps. So hopefully you recognized that negative 3x cubed over x to the fifth is the end behavior model. You might have missed the negative at first, so go back to the original function and just double check that you see why there's a negative on top. To actually complete the proof, here are the steps that I would have taken. And ultimately it shows, since the limit equals 1, that this is an end behavior model. Okay, so now that you are full of all this algebraic nonsense, I think it's time to go back and talk about why end behavior models are worth all the trouble they take to prove. So here are 5 kind of basic functions. And looking at these functions, I want you to guess an end behavior model for each of them. In fact, I'm going to put it in an Edpuzzle question for you. Cool. So I imagine it was easy to guess the end behavior models for A and B. They're pretty similar to the ones we were talking about. Once you get to C, D, and E, though, something goes wrong. In particular, just the simple pattern of using the highest degree term, or the 2 highest degree terms, doesn't work anymore because we have these weird functions. So we actually need to take a step back and talk about why end behavior models matter, and then use some extra strategies. We'll do that in the next video.